so we want to determine whether each series converges or diverges. And write complete sentences for the conclusions. Right, 5 root n over 4n squared plus 7. So the closest sum that I can compare to whose convergence or divergence I know, I'm just going to look at the leading, just going to look at the leading terms here. The ratio of the leading terms, I can ignore the coefficients when I'm trying to come up with a comparison integral. So I want to compare to the sum of root n over n squared, which is going to reduce to n to the, that's n to the 0.5 over n squared, 1 over n to the 1.5, which converges because it's a p-series test. It's a p-series with p bigger than 1. All right, so I can either use the direct comparison test or the limit comparison test. I always recommend the limit comparison test. It is a little bit easier. Okay, so I'm going to compare the limit as n goes to infinity of my series, 5 root n over 4n squared plus 7, divided by my comparison series, 1 over n to the 1.5. Limit as n goes to infinity. Okay, so I have 5n to the 0.5 over 4n squared plus 7, and I'm going to multiply by the reciprocal, n to the 1.5 over 1. So the limit as n goes to infinity of 5n squared over 4n squared plus 7. And this is a rational function. The limit as n goes to infinity. The degree of the numerator and denominator is the same, so the limit is the ratio of the leading coefficients, 5/4. All that needs to be true about this limit is that it has to be non-zero and finite. So since 5/4 is non-zero, and 5/4 is not infinity, my sum has the same behavior as the comparison sum. So the sum from n equals 1 to infinity, 5 root n over 4n squared plus 7 also converges. Okay, this time I have a sum of n to the 6th times 3 to the n over n plus 1 factorial. Anytime you see exponentials and factorials or factorials, you want to head right for the ratio test because we're going to have some nice cancellations happening if we use the ratio test. So with the ratio test, I take the limit as n goes to infinity of the n plus first term, which would be, means replace all your n's with n plus 1s, n plus 1 to the 6th times 3 to the n plus 1 over, if I'm replacing this n with an n plus 1, that becomes n plus 1, which is n plus 2 factorial. Then I divide by the nth term, n to the 6th times 3 to the n over n plus 1 factorial. So now I'm just going to flip and multiply. So I have n plus 1 to the 6th times 3 to the n plus 1 over n plus 2 factorial times n plus 1 factorial over n to the 6th times 3 to the n. So now I'm going to simplify. This is the limit as n goes to infinity. Okay, so my 3 to the n plus 1 over 3 to the n, that is going to reduce to 3 on top. So n plus 1 minus n is 1, so this becomes 3 to the first. Okay, and then n plus 1 factorial over n plus 2 factorial. It might help to write out a couple of terms. So n plus 2 factorial is n plus 2 times n plus 1 factorial, and then my n plus 1 factorials cancel. So I'm left with 3 times n plus 1 to the 6th over n to the 6th times n plus 2. All right, so this is the limit as n goes to infinity of, when I raise n plus 1 to the 6th power, the leading term is going to be n to the 6th. So I have 3n to the 6th plus some lower order terms, some n's to lower powers. And in the denominator, I'm going to distribute my n to the 6th to my n plus 2, and I get n to the 7th. And the lower order terms of n don't really matter, lower order powers of n. And then the limit of this rational function, n to the 6th over n to the 7th, the denominator is bigger, which means that this limit is going to go to 0. Okay, and the ratio test says that if that limit is less than 1, then my series converges. Less than 1. So my series converges. So by the ratio test, my sum, which was n to the 6 times 3 to the n over n plus 1 factorial, converges. Okay, so for this one, this is really close to a p-series. I want to compare to the p-series 1 over n cubed. Which converges. Okay, so if I'm comparing to a p-series, that means I should do a direct comparison or a limit comparison. Again, I like the limit comparison test a little bit better. So I'm going to take the limit as n goes to infinity of my series, 1 over n cubed plus 7n squared minus 9, divided by the comparison series, 1 over n cubed. And I'm just going to do my flip and multiply trick. So this becomes the limit as n goes to infinity of n cubed over n cubed plus 7n squared minus 9. And then I'm just taking a limit of a rational function where the degree of the numerator and the denominator are the same. So I get the ratio of the leading coefficients, which is 1 over 1 or 1. Now, the limit comparison test says that that limit has to be finite and non-zero. And if that's the case, if you get a finite non-zero limit, then the two sums have the same behavior. The one you don't know has the same behavior as the one you do know. So, since one is finite and non-zero, my sum of 1 over n cubed plus 7n squared plus 9 minus 9 converges just like my comparison sum, 1 over n cubed, converges. Okay, this one is just a little bit tricky. You might be tempted to compare this to 1 over n, maybe. But if you just look at the leading terms, the square root of n squared is n, and then the denominator has a highest exponent of n to the first. So there isn't an obvious comparison to a p-series. And the fact that the numerator and denominator have the same degree means that the limit as n goes to infinity of the square root of n squared plus 7 over 2n plus 3. When n is really, really big, this is equal to the limit as n goes to infinity of the square root of n squared over 2n. I just have to look at the leading terms, which is equal to the limit as n goes to infinity of n over 2n. N's cancel, and I get 1/2. So because the terms approach a half, this fails the nth term for divergence test, right? So this series diverges, but let's just talk about y for a second. So the sum of this thing, n squared plus 7 over 2n plus 3. If I plug in a 1 here, I get the square root of 8 over 5. Right? If I plug in a 2, I get the square root of 11 over 7. Plug in a 3. 3 squared is 9, plus 7 is 16. I get the square root of 16 over 2 times 3 is 6, plus 3 is 9. Okay, so the fact that as n goes to infinity, my terms are going to a half means that I can skip a bunch of numbers here, and eventually these are going to be like adding a half over and over and over again, which means that I'm going to be increasing the value of this sum every time I add something on. I'm going to be increasing it by a 1/2. So I'm going to increase the value of this sum without bound. It's just going to get bigger and bigger and bigger and approach infinity. So because the limit as n goes to infinity of the terms because that equals a half, not 0, the sum diverges by the test for divergence.